Evening, everyone. Welcome to the 10th live session for the course Concrete Technology offered by NPTEL. So, I am Harshit Agrawal, a PRMRF scholar from the Department of Civil Engineering, IIT Bombay, and I will be conducting weekly live session for the entire course duration. So in today's session, we'll first revisit the last live session that was about the week 9 content in a quick recap manner, and then we'll look into the things that are covered in the week 10 content of the course. So the week 10 content that we'll discuss today will be about durability of concrete. So for this session, the discussion is divided into following sections. So first we'll talk about a basic overview of durability and service life. Then we'll touch a little bit on repair, retrofitting, and rehabilitation of concrete, what these terms actually mean. Then we'll talk about different ways in which concrete degradation happens, and then we'll specifically move into chemical related degradation, where we'll talk about sulfate attack, acid attack, alkali aggregate reaction, and freeze and thaw attack. After this, we'll have a brief discussion on corrosion. What is corrosion? Why corrosion occurs? How corrosion damages a reinforced concrete structure? And we'll touch up a little bit upon carbonation and chloride induced corrosion. In between, I will have some objective questions. So there will be around 15 to 16 question in total that will challenge your understanding about the concept. And finally, we'll conclude the discussion and I will try to address any other query post discussion. So if you have any doubt, you can type in the chat box or you can unmute and speak. And if there's any problem in the connection while I'm teaching, so just unmute and speak and tell me that the network was not there in between. So last week we concluded the ninth week of the course where we continued our discussion on mechanical properties of concrete by discussing about modulus of elasticity of concrete. In this we discussed what is modulus of elasticity. Basically it is the ratio of stress versus strain in the linear elastic region. Okay, then we discussed why concrete shows a non-linear inelastic behavior in a stress strain relation. We talked about different types of modulus of elasticities of concrete, which included tangent modulus, secant modulus, chord modulus, and initial tangent modulus. We talked about different ways in which modulus of elasticity can be measured using static method and dynamic method. We talked about different types of modulus of elasticity based on direction of deformation, and we talked about how concrete properties affect the modulus of elasticity value. Then we talked about fatigue in concrete, why fatigue occurs, and two types of fatigue deformation, that is creep fatigue and cyclic loading fatigue. So creep fatigue is basically when the load is applied for a very long duration at a slow rate. Okay, so in that case, the low stress in concrete is significantly lower than it should be, and there is a large deformation in concrete. While in cyclic loading fatigue, it is like load is applied, then it is unloaded, then loaded, then unloaded. So in this way, there are cycles of loading on a structure, which brings a lot of strain development in the structure. Then we discussed about bond strength of reinforced concrete and what are the critical properties on which bond strength depend. So it is the chemical adhesion, mechanical interlock, and the friction between the reinforcement and the cover concrete. We saw how concrete and reinforcement properties they affect the bond strength, and how bond strength is determined using a pull-out testing. So this was the UTM framework in which this is a pull-out frame, and we saw how this frame is able to estimate the bond stress versus slip profile. And then we discussed about creep in concrete. What is creep? Basically, it is deformation due to sustained loading, and we understood that using a stress strain relationship. So, when we have a constant stress applied over concrete, over time the strain it increases beyond initial elastic strain. Okay, so this increase in strain beyond initial elastic strain, this is known as creep. We saw about how what is creep recovery and creep relaxation. We talked about how concrete property affects the creep in concrete, and we then moved into how creep can be predicted from past or present data. So for this, first using ACI 209 model, where creep coefficient is determined after a time t in loading, where load is applied at a time t naught. So we saw how creep coefficient is estimated. So for this, we have it is based on ultimate creep coefficient, which takes into account different material properties like age of loading, relative humidity, volume to surface area ratio, slump factor, fine aggregate ratio, and air void content. So based on all these factors, we get the ultimate creep coefficient, and then based on the time till which the structure is loaded, we get the creep coefficient after time t, which gives us an indication of how much creep has occurred in concrete. Okay, so one of you asked, I guess, in the YouTube video, how we get this ultimate creep coefficient and whether all these values will be given or not. So basically, if this question is asked in exam, they will give all the values, or they will directly give you the ultimate creep coefficient, or they will give all the relationships that you can see here to you, so that based on the structural properties, you can estimate all the factors, and then you can calculate the ultimate creep coefficient. But I think so in exam, if it is asked, then directly ultimate creep coefficient will be given to you, and you just need to calculate creep after a time t. Just like how we did one numerical in the last session. Okay, like that it will be asked. Then they using BS method, there is a standard correlation chart where creep coefficient is estimated based on the concrete age of loading, relative humidity, and volume to surface area ratio. After prediction, we saw how creep is measured in laboratory condition based on ASTM C512 method. So in this concrete cylindrical sample, they are subjected to sustained loading between two frames, and the deformation in each concrete, it is measured using a deflexometer. Okay, that will give us an indication of strain, how strain is increasing over time. After creep, we talked about shrinkage, where we first discussed about different types of shrinkages, mainly plastic shrinkage, which occurs in fresh state, drying shrinkage, which occurs in hardened state, autogeneous shrinkage, which is a basic shrinkage which will occur due to hydration of cement. When it reacts with water, the volume decreases. Okay, so that is autogeneous shrinkage, and carbonation shrinkage, which can happen due to CO2 interacting with portlandite. Similar to creep, using ACI 209 method, we saw how shrinkage is predicted based on ultimate shrinkage coefficient, which takes into account material and environmental factors into consideration. And for all these factors, we saw how different correlation charts or tables which are given in ACI code to estimate the ultimate shrinkage coefficient. Then, similar to creep, again we have BS method, where based on the volume to surface area ratio and relative humidity, we can predict the shrinkage after 6 months or after an infinite time. Okay. Finally, we discussed how we measure the shrinkage. First, using a length comparator, which gives us an indication of drying shrinkage. Then we talked about autogeneous shrinkage, which can be measured using ASTM C1608 method, and a ring constraint shrinkage method based on ASTM C1581. Okay, so this was our discussion from the last session. uh, Whenever there is an flaw in connection, like, just unmute and speak, because I continue teaching and I see that the connection went off, and then I'm not able to uh, track back at what point the connection went. Can anyone tell me where was I when the connection broke? Hello, am I audible to everyone? Can any one of you unmute and tell me at which point connection went off? So I was just discussing about measure what all things we have discussed in the previous session. So we started with elastic modulus, then we came to fatigue, then we talked about bond strength, then we talked about creep in concrete, how we predict creep and how we measure creep, and then we talked about shrinkage and prediction and measurement of shrinkage. Okay, so till date, we have talked about individual components of concrete, mixture design, and mechanical properties of concrete. Now, the final segment of concrete discussion is about durability of concrete. Now, when we talk about durability in modern day construction application, is has strength a sufficient parameter for designing a concrete? The answer is a clear no. Why? Because there are several evidence of raising cases of premature failure of concrete due to degradation. And that's why durability of concrete has become an important factor as important as strength of concrete. Okay. So now, what is the technical definition? Like, what do you mean by durability? So, if we see the definition of durability given by American Concrete Institute, so durability of concrete is defined as its ability to resist weathering action, chemical attack, abrasion, or any other forms of process of deterioration. Okay, so this is evident from raising cases of failure that due to interaction of concrete with its surrounding, there are deterioration in concrete. So that's why American Concrete Institute defined durability as the ability of concrete to resist weathering action or any kind of deterioration measures. Okay, so this is what durability mean. Now, how we define whether concrete is durable or not? So, if we see Indian standard definition, a durable concrete is defined as the one which performs satisfactorily under a certain exposure condition for a specified service life or a lifespan of a structure. So, both these definition they are defining the same thing. They are defining the durability of concrete but from different angle. So the first definition given by ACI, it talks about durability, what durability means, that is resistance to weathering action, whereas the second definition that is given by Indian standard, it says how it it talks about response of concrete to this weathering action as the definition of durability. Okay, so if you see, I have highlighted one word on this slide, that is service life or lifespan. So it's not like I have prepared a concrete and now it will last for a lifetime. No, concrete will naturally degrade over time, and this natural degradation is what we consider during the design of concrete in terms of service life. Okay, so service life of a concrete, it is nothing but an assumed period for which structure or a part of it is to be used for the intended purpose with specific maintenance but without any major repair requirements. Okay, so service life is, it's like when we design a concrete, we fix the service life. Suppose we want a structure for 100 years or 50 years or 150 years, so this is the intended service life from the structure. Now during this period, I assume that my structure will be able to perform its intended purpose. So if a structure is built to function as a laboratory, it should work as a laboratory only. If suppose after 25 years the structure's functionality got degraded and we changed it from a laboratory to a war to just a storage space, then also the service life has ended, because for the purpose for which the structure was made, it is not being used anymore. So service life is the part, is this time period until which the structure is able to serve its intended purpose with minimum maintenance required. Okay, and no major repair requirement. Okay, so this is service life. Now, so this figure here explains the degradation, the deterioration, and what is service life. So if you see this gray dotted line, this gray dotted line shows how performance of a concrete naturally degrades Okay, so initially the performance of concrete was at this level. Okay, from by performance it can be mechanical performance, any form of mechanical performance of the structure. Okay, now due to exposure to environment and due to ingress of aggressive agents from environment, slowly the concrete is degrading. So this line represents the loss in performance over time. Now I have defined a critical performance limit. Okay, so below this, if the performance of structure goes, then I will say that the service life has ended. Okay, so you can see this degradation will happen, and after a certain time period we will reach this critical performance limit. Okay, when we'll reach this critical performance limit, we will say that the performance of service structure has gone below the critical performance limit, and thus it has reached this service life. Okay, now this is a kind of degradation that is like pre-planned. Okay, that we have already planned and we know, okay, my structure will serve for 100 years. But if there is some extra unplanned degradation that is occurring in concrete, the performance drop will be faster than expected. Okay, so it will reach this critical line earlier than expected. So there will be a loss in structural life due to deterioration. Okay, so this is due to interaction of structure with the chemical environment. Okay, and we are not able to meet our anticipated service life. I wanted a service life of 100 years, but due to the severity of exposure conditions, my service life came to 70 years or 60 years. Okay, this is due to degradation of concrete. Now, how to counter this degradation? And to counter, we have repair, rehabilitation, and retrofitting. Okay, techniques. So after timely interval, so this is my structure response. Okay, and I want a service life of this value. Okay, right now it is suppose 70 years, I want a service life of 100 years. So after different time intervals, I will do some repair, retrofitting, or rehabilitation measure on the structure to increase the performance of the structure. Then again it will degrade, then again I will do some repair, retrofitting measure, then again the performance will increase. So in this way, with minimum maintenance requirement or with some major repair requirement, we can increase the service life of our structure to the intended life that we wanted. Now this is just an additional point that I'm discussing here, which is very important to clarify at this stage, and that is to understand the difference between these three R's, that is repair, rehabilitation, and retrofitting. So when it comes to existing buildings or structure, there are three strategies that can be opted to for durability concerns. The first is repair. So repair means to restore the structure to its original condition. So suppose there is a structure which has degraded. So by repair, what we mean, we are again restoring the structure to its original condition. Okay, how this is done? By replacing damaged element, by restoring lost feature, or by repairing system which aren't functioning anymore. Okay, what is the advantage of repair? It is cost effective and quick. Okay, better than replace. It is better to repair rather than to replace. But the disadvantage is it doesn't address the age related issue. So over time, when certain functionality ends in the structure, that can't be repaired. Repair can only be done to restore the properties. The repair is only possible for those properties that can be restored. Okay, then second is retrofitting. So what retrofitting means, the aim of retrofitting is to adapt to a new use. So suppose a structure was designed to serve for a load capacity of 70 MPa. But now, due to increasing traffic load or due to increasing footfall on a structure like a high rise building or a bridge, in terms of traffic, instead of 70 MPa, I want the structure to bear a stress of 100 MPa. So I want my structure to adapt to a new use. So for those conditions, I will go for retrofitting. So retrofitting is modifying the existing structure to suit a different purpose. Okay, and what is the advantage? It increases the functionality of the structure. Okay, so instead of serving as a M70 grade material. Now my reinforced concrete will serve as a M100 grade material. Okay, what are the disadvantage of retrofitting? It can be expensive and time consuming. Then the third is rehabilitation. So rehabilitation is bringing a structure up to current standard by adding modern features or system. So I have a structure which has degraded, but still I will do some m- uh, conservative techniques so that that building is suitable for current use. Okay, so how this is done? This is done by modifying the structure for safety, comfort, and efficiency. Though the structure has degraded, but I will try to make the structure safe and comfortable for its user. That is known as rehabilitation. Okay, what rehabilitation does? It enhances the safety, comfort, and efficiency. But what is the disadvantage? It is time consuming and sometimes it can be expensive. Okay, so all these three R's, they have different purpose when we talk about action against degradation of concrete. Okay, so repair and retrofitting we can understand from these two figures also. So suppose I represent deterioration on y-axis and time, deterioration in performance on y-axis and time on x-axis. So we know the deterioration will increase over with time and the performance of a concrete, reinforced concrete, will decrease over time. Now what does repair do? It increases the durability of concrete. Okay, so we saw here we are restoring the structure to its original condition. In original condition the concrete was not degraded, so we are again increasing the durability of concrete. So we are not doing anything with the strength of concrete, we are just increasing the durability of concrete. So when we increase the durability of concrete, we are slowing down the rate of deterioration of concrete. As we'll slow down the rate of deterioration of our structure, eventually we'll end up increasing the life of the structure. So this is the purpose of repair. And what does retrofitting do? So in retrofitting, we are increasing the strength of concrete. Like we discussed, from 70 to 100 MPa we are going. So we are increasing the performance of the concrete. Okay. When we increase the performance, we in turn increase the durability of concrete, and thus we increase the life of concrete. Okay. So this is the use of retrofitting. I just need to check my connection regularly. So on this slide, we have a basic flowchart that describes both definitions that we talked about durability. Okay, so durability is a function of both concrete system as well as aggressiveness of the environment. In concrete system, it is governed by the quality of material, okay, which is dependent upon both the materials that are used in concrete, like the binder type, binder content, aggregate, admixture, and mixture design. So all these components, they define what is the grade of my concrete, what is the porosity in my concrete, how well the concrete is suitable for the intended exposure environment. Like we saw in IS 456, there is table that is designed for different severity of exposure condition. There is a table, there are different conditions that were mentioned where for minimum grade requirement, maximum minimum water to cement ratio that should be used, maximum cement content that should be used. So material defines whether our structure is suitable for those durability criteria or not. Then the process of mixing after post mixing, which includes mixing, transportation, compaction, curing, temperature, and workmanship. So all these processes we have seen, they can affect the condition of our concrete in terms of any forms of honeycombing or cracks or voids if all these processes are not done properly. So we have talked like from mixing to pouring, the concrete should be below its initial setting. Okay, so if we pour the concrete below its initial setting, then it will spread homogeneously and there won't be any major voids in the concrete. But suppose there is delay in transportation or there is improper compaction, then there will be big voids in concrete which will raise the durability issues. Or if curing is not done properly, so though we have chosen all the material compositions properly, still the concrete won't gain enough strength. Okay, so in this way process can also define the durability of a concrete. And Aggressiveness of the environment, it dictates the degradation rate of concrete. Okay, from in terms if from aggressiveness, it can be either physical, like abrasion, erosion, cavitation, or freeze thaw action that occurs over a concrete surface, or it can be chemical. So different types of chemicals, they may enter the concrete due to dissolution, leaching, expansion, or alteration, and they can cause degradation of concrete over time. Okay, so on this slide, you can see few examples of how a concrete system in terms of quality of concrete can affect the durability performance. So as an exercise, can anyone tell me what all these three figures represent? What type of degradation these three figures are representing? Just give it a try. And in the meantime, if you have any doubt regarding any discussion that we had right now on durability, you can ask. So just tell me what figure 1 tells, what figure 2 is showing, and what figure 3 is showing in terms of degradation of a reinforced concrete. What type of degradation it is? All the three figures, they are representing cases of poor quality concreting, which can occur due to poor workmanship or poor handling of concrete on site. Okay, you just need to tell me what kind of durability issue you see in this structure. Any guesses? What figure 1 shows? So figure 1 here represents the shows presence of big voids, surface voids on the surface of this reinforced concrete element. Then these voids, they are known as honeycombing. Okay, so these voids, they arise mainly due to poor compaction of concrete. So suppose I have prepared a concrete, and from mixing plant to pouring plant, while transportation of concrete, the concrete already started setting, or maybe after pouring the concrete inside the formwork, it was not given proper compaction. So such things, they can give rise to big voids on the surface of concrete. Okay, and these voids, make the they will ease the ingress of aggressive chemicals from the surrounding to inside the concrete structure, which will raise durability concerns in concrete. Okay, so this is first image. It represents honeycombing. Now can you even tell me what second image represents? What type of durability concern can you see in the this one?
No cover, less cover due to dust, reinforcement got a corrosion.
So the second image shows the case of a corroded reinforcement inside concrete, which came up earlier than expected, maybe due to inadequate cover thickness. So when we talk about concrete, we talk about the cover thickness also, how much cover we need to provide to a reinforcement. Suppose the contractor was supposed to provide a cover thickness of say 40 mm or 50 mm, but he provided only 25 mm. So based on the severity of exposure condition, that cover thickness may not be adequate to serve the concrete life of 100 years, because corrosion occurred way before the expected time, and that led to spalling and delamination of concrete cover. How this happens, what is corrosion, we'll discuss later, but this is just a case that you can see this degradation is due to corrosion of embedded reinforcement. Now, just think about the third image. What third image shows? What type of degradation this in this third image is representing? Yes, second one is less cover. Third is less bonding. Why you see this as less bonding? Any particular reason? Where is bond? So this is complete concrete wall, okay, and there is a longitudinal cracking line that you can see. We have discussed this image before also. Just think. So this shows the case of cold joint, which arises due to delayed pouring of a second batch of concrete over the first batch. So if you remember, we had the discussion multiple times before. I am pouring a concrete in a wall. Okay, suppose in one batch I was able to fill half of the height of wall. Then I am pouring the second batch of concrete, but there is a long gap between the first pour and the second pour, due to which the first pour already settled, and when we pour the second batch of concrete, then there will be some voids that will be created at the interface of the first pour and the second pour, and these voids, they are known as cold joint. Okay, so this is the case of cold joint, and all these three, they represents a case of poor quality concreting that may arise due to material, or they that may arise due to post mixing operation. Okay, yeah. Now, talking about degradation of concrete due to surrounding, it can happen in several ways. Okay, so there is mechanical degradation which can happen due to abrasion. So, abrasion is an issue which you can observe in road pavement due to moving vehicle, the rubbing of the tires and the concrete pavement, they cause abrasion, they cause degradation of concrete surface. Then erosion happens near seashore. There is impact when there is certain drop of massive load on a concrete structure, that can cause cracking in concrete, localized erosion or degradation of concrete. Explosions can cause degradation of concrete. Then there are physical degradation due to freeze thaw action that we have seen already, how they cause cracking. Shrinkage and creep can cause cracking in concrete. Fire again is a case where degradation can occur because water, it converts into vapors. Now concrete is not that porous, so vapors won't find easy part to get released. Okay, so the more vapors they will form inside a closed space of concrete, they will give rise to vapor pressure, and those pressure can cause cracking in concrete. Then the structural degradation due to overloading. So suppose I wanted to design a concrete of M55 grade, but by some mistake in concrete quality or concrete batching, the concrete came out to be M30. So due to this mismatch of concrete grade, this M55 MP stress will be kind of a overload on this concrete, which can cause cracking in concrete, which will be a form of structural degradation. Settlement issues can rise if the underneath soil below the structure is not able to take enough load on the structure, so the soil will settle down and it will bring cracking in concrete. Then there's fatigue cracking, which is similar to the creep effect that we have seen. Then there's chemical degradation that we'll talk in today's session, that can be due to alkali aggregate reaction, acid attack, or sulfate attack. Biogenic degradation is there due to fouling or biogenic attack, like you see K patches on concrete walls. Okay, and then there is corrosion of embedded steel reinforcement. So today we'll be discussing about chemical degradation and corrosion. Now both these categories, chemical degradation and corrosion, they involve the presence of moisture as a key agent to contribute to the ingress of chemicals and aggressive ions. Okay, so lower is the permeability of concrete, better is the resistance to aggressive environment. Okay, all these chemical and corrosion related degradation, for them moisture is key. Okay, when aggressive ion enter the concrete structure, they need moisture also with them. They enter in the presence of moisture. Okay, so if my structure is less permeable, the moisture penetration will, so my concrete will have more durability against aggressive chemicals. Okay, just try to answer these three simple questions now, and in the meantime, if you have any doubt regarding our discussion on durability and degradation of concrete, you can ask. Okay, so the question one says, which of the following statement is true regarding durability of concrete? So just think about the definition of durability that we have talked in detail till now, and try to answer this question. Any guess? Okay, C. Yes, C is the correct answer. So, use of supplementary cementitious material, it enhances the durability of concrete by reducing the permeability. So, just now we have talked about how moisture plays a critical role in the ingress of aggressive ions. So, when we use supplementary cementitious material, we have seen that it converts the Portlandite into calcium silica hydrate. Portlandite, it contributes to the porosity of concrete. Okay, but by adding supplementary cementitious material, we are densifying the concrete. When we densify the concrete, we'll reduce the permeability of concrete, so we'll enhance the durability of concrete. Question number two, which factor has the greatest impact on long-term service life of a reinforced concrete structure? Any guesses for question number two? If you want, you can unmute and speak also and give me an explanation why you think a certain option is correct. Yes, the correct option is B, exposure condition and permeability. So, as we have talked in IS 456 also, concrete durability, it is primarily controlled by its ability to resist aggressive agents like water, chlorides, and sulfates. And how aggressive is the environmental condition defines what is the need, what is the need for durability in from concrete. Okay, and the permeability of concrete also, it plays a very important role. That's why in is code we have control over the water to cement ratio and grade when we talk about severity condition of exposure severity conditions. Okay, these two factors, they together they contribute the greatest in terms of long term service life. Question number three. In retrofitting of concrete, so retrofitting means increasing the functionality of concrete, increasing the strength of concrete. Fiber reinforced polymer wrapping are primarily used to. So if you have seen on big bridge piers, there is carbon wrapping done across the appears. Okay, so those carbon wrapping, black carbon wrapping, those are fiber reinforced polymers. Okay, so those wrapping, why they are done, to how they enhance the retrofitting of concrete. Any guess for question number 3? Okay, the correct answer for question number 3 will be B. They improve the ductility and the flexural strength of concrete. Okay, so when we talk about FRP wrapping, it enhances the load carrying capacity of the structure. It enhances that, then that is the purpose of retrofitting. Okay, so when we enhance the load carrying capacity of the structure, we eventually enhance the ductility and the flexural strength of the structure also. So wrapping, it can be done on both, like on columns we do wrapping to increase the confinement. When we increase the confinement, we eventually increase the strength of concrete. And on beams also, you will see wrapping layers are placed at the bottom. So when we place this FRP wrapping layer on the bottom, we eventually enhance the flexural strength or the tensile capacity of our reinforced concrete. Okay, so in any way we are enhancing the functionality of concrete. That is the purpose of retrofitting. So one of you unmuted. If you have doubt, then only unmute. Okay. Now let's start our discussion about chemical attack. Okay. So in chemical attack, we'll first discuss about sulfate attack in concrete. So what is sulfate attack? So sulfate attack is basically a reaction between sulfate ion and hydrated cement product. Okay. Now there can be two forms of sulfate attack. There is external sulfate attack and there is internal sulfate attack. Okay. External sulfate attack means sulfate ions are ingressing into the concrete from groundwater or seawater, or due to bacterial actions from sewers. So I have a concrete structure, hardened concrete structure, and from outside sulfate ions are ingressing into the concrete and they are degrading the concrete. So that is external sulfate attack. And internal sulfate attack, it occurs due to late release of sulfates within the concrete, okay, which results in distress. Okay, and this is also known as delayed Ettringite formation. So I have a concrete structure, there is no ingress of sulfates from the surrounding, but the sulfates that are present already inside the concrete, they are causing distress in concrete. That is known as internal sulfate attack. Now, what is the end result of sulfate attack? It causes softening and loss of integrity of concrete. Okay, and that's why there are limits on sulfate degradation in IS 456. Okay, so IS 456 code says that the total water soluble sulfate content in concrete, as expressed in SO3 percentage, should not exceed 4% by mass of cement. Okay, and aggregate should not contain more than 0.5% of sulfates as SO3. Okay, so that's why there are limits that are mentioned in IS code, because sulfate attack can be a serious degradation issue for concrete. Now, first, how external sulfate attack occurs. So basically, each hydration product can give rise to a new compound because of sulfate attack. Now, the primary products that form due to sulfate attack, these are gypsum and ettringite. Okay, so in the first equation, you can see we have portlandite, which is there inside the concrete. It reacts with sulfate ions in the presence of water to form gypsum. Now, in the second and the third equation, you can see ettringite formation is occurring from when these sulfate, it reacts with monosulfates or C3 phase. Okay, so from these two equation you can see that this is the hydrated cement paste and this is the unhydrated phase in my cement. Okay, this is the external sulfate ions that came interacted with calcium hydroxide and form calcium sulfate. Okay, they reacted with the cement hydration, hydrated phase to form a new compound, that is ettringite. Now what is the problem here? So if you observe the second and the third equation, this reaction consumes a lot of water. Okay, due to which swelling happens, and thus because of the formation of ettringite, which has a high surface area, it gives rise to cracking and disintegration of hardened concrete. Okay, why? Because we don't have enough free space in concrete to confine such a high surface area product. Okay, to accommodate such this swelling pressure, and thus there is disintegration or cracking inside concrete due to sulfate attack. Now, there are other reactions also that can happen, which can cause progressive loss of strength of structure. Okay, so sulfate ions, rather than just affecting the monosulfate group or the C3 group, it can affect the calcium silica hydrate product also. How? So this CSH there, it is only affected due to action of magnesium sulfate. So if there is magnesium sulfate ingressed into the concrete, it reacts with CSH to form gypsum and serpentine. Okay, and this serpentine magnesium ion it replaces the calcium ions from the CSH structure. It has a it has a poor crystalline. It is a poor crystalline material. So it will the concrete will lose its ability to hold all its constituent together, which was due to CSH degradation. Okay, so that in that way also there will be disintegration of concrete. Okay, so this is how external sulfate attack occurs. We are still discussing about sulfate attack. Was there some connection issue? So this part I am explaining what is external and what is internal sulfate attack. I just gave you an overview on this slide number 23 that sulfate attack is a reaction between sulfate ion and hydrated cement product. It can happen due to it can happen in two ways: external attack or internal attack. External means sulfate ions are coming from exterior to inside concrete. Internal means the sulfate that are already present inside concrete, how they are degrading. Okay, and in both case we will see cracking and loss of integrity of concrete due to sulfate ions, and that's why is code has posed limit on how much sulfate there should be inside concrete when we do batching of concrete, because excess of sulfate inside concrete can give rise to degradation issues in concrete. And then on slide 24, we started discussing about each of the categories. What is external sulfate attack and what is internal sulfate attack? So external sulfate attack, the sulfate ions reacts with different hydration products to form ettringite. And this formation, it consumes a lot of water. So there is swelling action that is occurring. Now we know that concrete has very confined structure, it has a very limited porosity. So such high pressure, high surface area product will give rise to swelling pressure inside concrete, which will lead to cracking and disintegration inside concrete. Okay, so this is how sulfate ions from surrounding it affects the concrete structure. Sulfate ions can also affect calcium silica hydrate product if it is magnesium sulfate. So magnesium sulfate, it reacts with CSH to form serpentine. Okay, this serpentine degrades the CSH, and we know CSH is the main binding phase in a hardened concrete. So if CSH is gone, my concrete will become soft. Okay, and it will lose the integrity. Okay, this is external attack. I hope it is clear now. Any doubts now? If you still have any doubt, just mention me the specific point which you were not able to understand and we will discuss. Okay. Now we here we talked about external sulfate attack. Now is the case of internal sulfate attack. So internal sulfate attack, it is also known as delayed Ettringite formation. So in case of internal circuit attack, what is this delayed Ettringite formation? So it simply means that formation of Ettringite in concrete is occurring at later stage after initial curing period. That's why we say there is delayed Ettringite formation. Now, when such condition can arise in concrete, so it occurs when concrete has experienced a elevated early temperature during curing. Okay, so suppose initially I prepared a concrete sample and I kept it in curing in water, but there was very high temperature during curing above 70 degrees Celsius. So what happens? We have seen the hydration of C3A. Okay, in C3A initially it reacts with gypsum, okay, to form monosulfate, and monosulfate converts into ettringite. Okay, so these all things are happening when concrete is in fresh state. Okay, but when temperature is more than 70 degrees Celsius, the ettringite formation doesn't happen in fresh state. Okay, now in such condition of concrete, what will happen? The sulfate concentration inside the concrete will be higher for a unusually long period. Okay, so since Ettringite formation has not occurred, there are still sulfate ions that are present inside the concrete for a longer period. So later on, when the temperature comes down, once the concrete has hardened, the sulfates which has not reacted yet, they will react with this calcium and alumina containing phases, the C3A phase, and form Ettringite. Yes, I will start again. Okay, so what I was talking, delayed Ettringite formation, it means formation of Ettringite at later stages. Now, when such condition can arise, when concrete has experienced a elevated curing temperature. Suppose during curing, the temperature of the curing the temperature in curing room was more than 70 degrees Celsius. So in such case, what happens? We know that we have talked about hydration of aluminate phase. Okay, C3 reacts with gypsum to form monosulfate, which converts into ettringite. Now at such high temperature, what happens? Ettringite formation doesn't occur in fresh concrete. So what this will cause, so the sulfate concentration that is there in the pore solution, it will stay there only because it has not reacted. So at later stages, when the concrete has hardened and when the temperature comes down, the sulfate which was not able to react in fresh state, it will now react with the C3A phases to form ettringite. And we know that ettringite conversion of monosulfate to ettringite increases the volume. Okay, so formation of ettringite is a generate will generate expensive pressure, okay, in concrete. And in hardened concrete, we don't have much space to accommodate the rise in volume, and so that will cause cracking in concrete. And this delayed formation of ettringite, which causes cracking in concrete, it is known as delayed ettringite formation. Okay, I hope everyone are clear with delayed sulfate attack or delayed ettringite formation. Okay, it is just because ettringite formation is not happening in fresh state, it is happening in hardened state. And we have already seen in week 1 or week 2 of the content, when we talk about hydration of aluminate phases, that when monosulfate converts into ettringite, there is the volume of product is higher than the volume of reactants. And in hardened concrete, such increase in volume will give rise to cracking in concrete. Okay, and this is known as internal sulfate attack. Okay. Now, what is the effect of sulfate attack? You can see on this slide. Okay, so first image shows the cement aggregate interface. Okay, where there is a ettringite lining which is present. Okay, so you can see here, this is a microscopic image, and there is a ettringite lining which is present at the cement aggregate interface. And this is due to this has led which has resulted in 2.8% expansion, okay, due to delayed ettringite reaction. Okay, And in the second image you can see a case of submerged column, okay, in seawater which is experiencing bulging. So you can see here the column has experienced some bulging action, okay, due to expansive reaction that might be occurring inside the cover as a result of sulfate attack from seawater. Okay, so this is causing degradation or distress in the concrete column. Okay. Now, how can we prevent or delay sulfate attack? By using sulfate resistant cement which has low C3A content that can cause avoid the formation of Ettringite, which can delay the sulfate attack or prevent sulfate attack. By using SCMs which has low calcium hydroxide formation, which makes a concrete dense, which can lower the ingress of sulfate ions from surrounding. By making concrete impermeable, again by using SCM or by using a higher grade of concrete, or by using a low water to cement ratio. So we know water to cement ratio and strength are inversely proportional. So if we decrease the water to cement ratio, we will increase the strength of concrete, we will reduce the porosity inside concrete. So we will eventually increase the resistance against sulfate attack. I hope everyone are clear with the sulfate attack part. Okay, so after sulfate attack, we have acid attack. So there are variety of acid which can cause degradation of concrete, like we have nitric acid, we have acetic acid, hydrochloric acid, carbonic acid. All these can cause degradation of concrete, but the majority degradation is due to sulfuric acid, okay, which is commonly found in sewers, okay, where a lot of sulfide gas exists due owing to high large degree of microbial action. So what this does, sulfuric acid, it creates an acidic environment in concrete, which in which the primary cement hydration phases like CSH and ettringite, they become highly unstable. Once they become unstable, the concrete loses its binding ability and thus softening of concrete occurs. Okay. So gypsum formation occurs when sulfuric acid reacts with CH, and thus there is loss of integrity and softening of structure because of this the gypsum formation and because of destabilization of CSH due to acid attack. Because when acid attacks the concrete, it lowers the pH also, and at when pH decreases, the CSH, it destabilizes. Okay, so that can also cause softening of structure. So you can see here in this image, sewer water, they are rich in sulfide ions. Okay. Now these sulfide ions, they get released, okay, as a H2S gas. Okay. But now in the presence of oxygen, H2S, it converts into H2SO4, and this is what causes attack on the concrete lining. So in this is aerobic condition. Okay, so in aerobic condition, acid attack is happening. However, if there is no oxygen present, okay, then this H2S won't react with concrete directly. Okay, we need H2SO4, okay, sulfuric acid only, which can cause cracking in concrete. So that's why it is said that in anaerobic condition, there is no oxygen presence, there is no effect of sulfate ions on the concrete linings. But in aerobic condition, when this liberated hydrogen sulfide gas from sewage, it interacts with O2, it forms sulfuric acid, and these sulfuric acid, they cause degradation of concrete linings, okay, in sewer pipes. So in the first image, you can see one such example of sewage pipeline where concrete wall has experienced severe degradation. So you can see there are peel off zone which are present here. Here there is exposed rebar which is present here, and all this is due to presence of oxygen and H2S gas in the sewage lines, which is causing acid attack on the concrete surface. Now, how to prevent acid attack? Either by using a protective layer, surface treatment like epoxy coating or coal tar, which can prevent the ingress of H2SO4, or by using some antibacterial cement, which won't allow H2SO4 to react with cement hydration product, or by making concrete impermeable. Okay, all these measures can be taken to increase the concrete resistance against acid attack. So we have few questions now. In the meantime, if you have any doubt regarding sulfate attack or acid attack, you can ask. Oh, it again went off. So was this slide discussed? How acid attack is occurring? What is aerobic condition? What is anaerobic condition? I will keep my presentation not on slideshow mode, because when I go to slideshow mode, then I am not able to see whether the connection went off or not. So I will teach on this mode only. I hope every the slide is visible to everyone. Which slide you want me to repeat? 27 or 28? Can anyone of you tell me? Okay, so on 27 slide we were talking about acid attack. Now acid attack can occur due to variety of acids like nitric acid, acetic acid, hydrochloric acid, or carbonic acid. But the major one occurs due to sulfuric acid, which is commonly found in sewers. Okay, so what happens in sewer lines? There is sulfide ions which are present in sewage, which is liberated as H2S gas. Okay, this H2S gas, in the presence of oxygen, it forms sulfuric acid, and this sulfuric acid reacts with concrete and it degrades the concrete. How? So when sulfuric acid ingresses into the concrete, it lowers the pH of concrete, which will destabilize the CSH. And we know CSH is the main binding material in concrete. And this sulfuric acid, it will react with calcium hydroxide and it will form gypsum, which will again cause softening of structure. So in this way, sulfuric acid is degrading the concrete. But here oxygen presence is important, because sewage water, it is releasing hydro H2S gas. Okay, and for acid attack to occur, we need sulfuric acid. So H2S will convert into sulfuric acid only in the presence of oxygen. So in anaerobic condition where there is no oxygen, this sewage water won't be a problem, which contains H2S. Only in aerobic condition where there is oxygen present, degradation of concrete occurs due to sulfuric acid. Okay. So, and on this slide, you can see the end result of acid attack. So, there is peeling off of concrete lining, there is exposed rebar that is coming to the surface, all because of sulfuric acid reacting with the concrete. How we can prevent this? By using a protective layer on the concrete surface, which can prevent the interaction of H2SO4 with concrete, or by using some antibacterial cement, which may delay the reaction of H2SO4 with cement hydration product, or by making concrete impermeable by using HCMs or by using higher grade of concrete. Okay, so this is acid attack. Now, try to answer these questions, and in the meantime, if you have any doubt regarding acid attack or sulfate attack, you can ask. So, question number 4 is, what is the primary mechanism by which acid attack degrades the concrete? So, based on our discussion right now, can anyone tell me the answer? Can you tell me the answer for question number 4? Yes, the correct answer is B. Okay, so we have just seen right now, due to acid attack, there is degradation of calcium compounds, which are CSH and CH. Okay, they they incur degradation due to hydrosulfuric acid, and which causes softening of the concrete lining. Question number 5. Which environmental condition accelerates both external and internal sulfate attack? I will change my network to a different setting. So just think about question number 5 right now. Question number 4 answer was B. What will be the answer for question number 5? Now it won't occur. Which environmental condition accelerates both external and internal sulfate attack? No, A is not a correct option. Low humidity with high CO2 exposure. CO2 has nothing to do with sulfate ions. And low humidity, it is basically low humidity is a issue when we talk about shrinkage or creep. Okay, that will cause a lot of evaporation of moisture. Just think in terms of sulfate attack. Yes, the correct option will be B. Alternate wetting and drying cycles. Okay, so we have seen that in sulfate attack, in sulfate rich water, what will happen? Sulfate ion will ingress into the concrete during the wetting cycle, and during the drying cycle, this alternate wetting drying cycle, what it does, it causes sorption effect inside the concrete. So it will increase the diffusion rate of sulfate ions inside the concrete. Okay, so in this way, it will increase the risk of sulfate attack inside the concrete. It will accelerate external and internal sulfate attack, maybe because of drying cycles where it will allow oxygen, enough oxygen presence inside the concrete, which will contribute to internal sulfate attack also. Question number 6. So this is a question which is linking what we have discussed in week 2 content and what we have discussed in week 10 content. So for the given three types of ASTM grade, so I have three grades of cement: type 1, type 2, and type 5, and I have given you the data how much C3 is present on in each type. Please mark the curve which will represent which type of cement. Okay, so there is data about how much expansion has occurred inside the cement paste due to sulfate attack, and in three different types of cement system. So you need to tell me which curve represent which type of cement. So this first curve, it has undergone maximum expansion, and this third curve, it has undergone minimum expansion. So which type of cement represent first curve, and which type of cement is representing this third curve? Can anyone tell me? Okay, so I will just tell you the answer for this question. The first curve, in which you can see maximum expansion occurring due to sulfate attack, it will represent the type of cement which has maximum C3A content. Because we know higher is the C3 content, more is the risk of attringite formation, monosulfate formations, or attringite formation, which will give rise to sulfate attack. Then curve 2 will be something intermediate. So I have two more cement type left, type 2 and type 5. Type 5 has less than 5% C3A, so it will show the least expansion, while type 2 will be somewhere in between. Okay, so this is how different types of cement they can influence the uh, sulfate attack. Okay, so at a particular water to cement ratio, the swelling effect is directly proportional to the attringite formation, which is dependent upon the presence of sulfate ions and on the amount of aluminate phase that is present inside the cement. So that's why type 5 cement, the expansion is minimum, while in type 1 cement the expansion is maximum. Okay, because of the aluminate content. Yes, type 5 below and type 1 on the top. Okay, so this was about sulfate attack and acid attack. Now, the next is alkali aggregate reaction. Okay, so after acid attack, we come to alkali aggregate reaction. Now, what is this alkali aggregate reaction? So, this is basically reaction of alkalis with a certain type of aggregate. Okay, now alkali here, it comes from the cement, the chemical, the mineral admixture, or the impurities in concrete. Okay, and silica is coming from aggregates which are present in amorphous form. Okay, so that's we generally tell that we need aggregates which are inert in nature. However, if my aggregates are not inert in nature, if they have some reactive silica or reactive carbonate phase that are present, those reactive phases they can react with the alkalis that are present in the cement paste system and give rise to alkali aggregate reaction. Okay, so you can simplify this reaction like this: alkali ions they react with silica and carbonates that are present in aggregate in the presence of moisture to form alkali silica gel. Okay, and this gel is expansive in nature. So in a hardened concrete system, when certain some expansive product forms, it causes cracking in the concrete. Now, how this alkali silica reaction is occurring? So, first we have amorphous silica which is present in the aggregate. So, this yellow brown colored thing, this is aggregate, and that has amorphous silica. Amorphous means reactive silica. Okay, so this amorphous silica and aggregate we have, and during cement hydration, alkali ions are released in the pore solution. So we know when cement hydration occurs, alkali ions Na plus K plus they are released in the pore solutions. Okay, so first step is the release of alkali ions in the pore solution during hydration. Now, in the presence of this alkaline medium, the silica in the aggregates is it breaks down due to hydrolysis into silanol groups. So this SiO-Si bond which were there in the aggregates, it in the presence of water it converts into SiOH and SiOH bonds. Okay, this is due to presence of this amorphous silica in the aggregate. So step 2 is the initial hydrolysis of silica fraction in aggregate in the presence of highly alkaline solution. So this is step 1. Then we came to step 2. Then step 3 is the silanol group that is formed. It further breaks down in the presence of alkaline medium into SiO minus group. So from SiO-Si bond in aggregates, we came to SiOH bond in the presence of alkaline medium, which further broke down into SiO minus plus H2 in the presence of OH minus. Okay, so this there is a release of this SiO minus ion on the surface of aggregate due to hydrolysis. Now, this released SiO minus molecule, it is negatively charged, so it will attract the alkali ions which are positively charged. So there will be a kind of gel formation that will occur around the aggregate. So the released SiO minus molecule attracts the alkali cations in the pore solution to form a gel around the aggregate. Okay, and in the presence of moisture, this gel it swells up due to imbibition of water. Imbibition means absorption of water. So it will the gel that is formed due to the reaction of released silica from aggregate and alkali ions, it swells up in the presence of moisture. And this swelling pressure, it gives rise to cracking in concrete, which gives rise to alkali silica degradation due to alkali silica reaction. Okay, I hope everyone are clear with this process, how alkali silica reaction is occurring. Any doubt in this? So we have alkali ions which are released during cement hydration. Now the amorphous silica which is there in the aggregate, it first converts from SiO Si. First this SiO Si bond breaks into SiOH, and then it further hydrolyzes into SiO negative molecules. Okay, this molecule, this negative anion, it attracts the cations, alkali cations, to form a gel around the aggregate surface, and this gel, it absorbs water and expands and swells up. Okay, so when swelling happens, it exerts pressure on the concrete, which causes cracking of concrete. Okay, so the degradation due to this alkali silica reaction, it generally appears as map cracking. So whenever you see certain kind of map cracking over the surface of a concrete, it can be due to alkali silica reaction. Okay, so you can see in these two images the map cracking which is shown due to alkali silica reaction, and in the third image you can see the gel formation that is occurring at the aggregate surface. Okay, so this gel formation, it will cause cracking in concrete. Okay, similar to alkali silica reaction, there is alkali carbonate reaction also. So alkali ions in the concrete, it can react with carbonates that are present in aggregate to form magnesium hydroxide. Okay, which is expansive in nature. Again, so this again can give rise to alkali carbonate reaction. Okay, now, how we can prevent this alkali aggregate reaction? By alkali aggregate reaction, it includes both alkali silica reaction and alkali carbonate reaction. How we can prevent them? By using non-reactive aggregates, by using inert aggregates, by using low alkali cements or SCMs. Okay, if we have low alkali in the cement, then the risk of alkali aggregate reaction will be reduced, or by preventing water permeation by applying a suitable coating. So we have seen that swelling of alkali silica gel happens due to absorption of water. So if we have a very if we don't have water at the aggregate interface, cement aggregate interface, then that swelling pressure won't be created, so making a concrete impermeable can also prevent the alkali aggregate reaction. Any doubt in this part? If not, we'll continue. Now, the next and the final part in chemical degradation is freeze and thaw action in concrete. So, this we have already talked earlier also, when we inside the heading of frost action in some earlier session. So, what are the critical points in freeze and thaw action? Water expands by 9 to 10% upon freezing. So, we have discussed when water converts into ice, there is volume expansion by around 10%. The freezing point of small pores are depressed to a larger extent. So freezing point in bigger pores, it happens at lower temperature compared to smaller pores. So in smaller pores, freezing of water may happen at minus 10 degrees Celsius, whereas in the larger pores, freezing of water will start at 0 degrees Celsius only. So if concrete remains frozen throughout its lifetime, then it is not a problem. The deterioration happens only when there is successive cycles of freezing and thawing. Why? Because freezing, when water freezes, it converts into ice. Ice occupies more volume. Then, when ice occupies more volume, the remaining water that was there nearby, it starts to move. Okay. So unfrozen water, it experiences hydraulic pressure due to expanding ice, and this water, when it travels through the paste system, it generates internal stresses inside the concrete. So these internal stresses, they give rise to cracking in concrete because there is no space to relieve the pressure that is generated due to expanding ice. Okay, so that's why there is freeze and thaw action. Freezing is also important, thawing is also important. So longer is the path of flow of water, higher is the pressure generated, and if this pressure exceeds the strength of cement paste, then the cracking will occur in the paste. So you can see in the first image how this freezing and thawing can cause cracking of a rock. So water is collected in a crack that is present on the rock. Then when water freezes, it expands. So due to expansion, there is further cracking in the rock. Okay, now when this ice again converts into water, then what happens? Water penetrates deep in the crack. Then again, when water will convert into ice, expansion will occur, so it will again cause cracking in rock. And eventually, after repeated freezing and thawing cycles, there will be complete breakage of the rock. Okay, so that's why both freezing and thawing is important. And in the second image, you can see an example of concrete pavement. So water is ingressing inside, ice formation occurred. Ice formation is expansive in nature, it caused cracking in pavement. This will allow more water to ingress inside. Okay, again ice formation will occur, so that will cause cracking in pavement, and for eventually there will be settlement in pavement. Okay. And in the third image, you can see degradation of a concrete column due to frost action. So you can see there is complete map cracking that occurred on the concrete column, which caused such degradation due to frost action. How we can prevent this? By using air entraining admixture. So we have seen earlier also, we can create well distributed air voids inside the concrete, which can accommodate this expansive pressure that is created due to ice, which can release the stresses generated. Or by using a low water to cement ratio concrete. Okay, so if we lower the water to cement ratio, we are increasing the strength of concrete, we are increasing the resistance against the stresses that are generated inside concrete, and we are also reducing the pore size that are present inside the concrete. So as we reduce the pore size, the freezing becomes difficult, so freeze and thaw action will be difficult. Okay, now just try to answer these questions, and in the meantime, if you have any doubt regarding freeze and thaw effect or alkali aggregate reaction, you can ask. So question number 7 says, which of the following strategy reduces the risk of alkali silica reaction in concrete? Okay, can anyone tell me? We have already discussed preventive measures. So based on those measures that we discussed, just think what will be the answer. Can anyone tell me the question answer for question number 7? What is the strategy we should you adopt to reduce the risk of alkali silica reaction? So the correct answer will be C. Okay, by using low alkali content cement or pozzolanic material. So we have seen in alkali silica reaction, both alkali and silica are needed. So if you reduce the alkali content that is there in the cement, then we can reduce the risk of alkali silica reaction. Question number 8, which type of aggregate is most susceptible for alkali carbonate reaction? What will be the answer? Yes, the correct answer is limestone with high dolomite content. So we have seen that dolomite means it is a ore of magnesium. So magnesium, when it is present inside aggregate, it can react with the alkali ions to form magnesium hydroxide, which is expansive in nature, which will cause cracking in concrete. Question number 9. Which of the following properties improve the freeze thaw durability of concrete? Any guess for question number 9? Yes, the correct answer is A. Dense microstructure with entrained air voids. So entrained air void, they will ensure that the processes that is generated due to expanding ice, due to movement of water, that can be relieved. And dense microstructure will ensure that concrete has high strength and small pores. So if there are smaller pores, the freezing of water will be difficult. So freeze thaw effect will be nullified. Now, these two are like a case study questions that something has been given to you and you need to take action. You need to form strategy against that. Just think. Okay, so question number 10 says that you are using a locally available aggregate for project and petrographic analysis revealed that those aggregate have reactive silica. Now, which is the most suitable long-term mitigation strategy knowing that you can't replace the aggregate? Okay, so you know that the aggregates that are you are using are having reactive silica. Still, if you want to do concreting, what action, what strategy you should take thinking about long-term durability? Yes, the correct answer will be C. Use of low alkali cement to stabilize the reaction. Okay, so when we use pozzolans like silica fume or we use uh, low alkali cements, then what we do, we reduce the risk of alkali silica reaction, which will stabilize the concrete. Okay, against the formation of expansive gel. Question number 10. For the mix concrete mix using reactive aggregates in a dry hot environment, which of the following strategies reduces the risk of alkali silica reaction? So this is the same like question number 10. Both will have the same answer using a concrete which has low alkali content. Okay. So this was just to show you like based on case studies how different case studies question can also come up in exam. Okay. So if you read both the questions, they may sound different, but their final intent is the same. Okay, in one they have seen that you are using reactive aggregates in dry and hot weather, and they are asking you the strategies to reduce ACR. In the other one, they have again said the same thing about reactive aggregates, but in not directly. They have told that aggregates contain reactive silica. Okay, what is the strategy to use? So in both the case, answer will be the same using low alkali cement or any measure which can prevent alkali silica reaction. Okay, so this was just to show you how case studies can also be framed in exams for checking your theoretical knowledge that you got from the concepts. Okay. So I was supposed to start corrosion in reinforced concrete, but I don't think so. If we start, we'll be able to conclude well. So let's start this section in the next session, because corrosion is my PhD area. This is the domain in which I am doing my PhD. So this will, like, you can have a lot of interaction, question and answer rounds with me in between to clarify your doubts. So let's start this thing in a fresh session, and let's end today's session at this chemical attack discussion. Okay. So in today's session, we discussed about durability, service life, and repair maintenance of concrete. We talked about degradation of concrete, about chemical degradation due to acid attack, sulfate attack, alkali aggregate reaction, and freeze thaw time. Okay. So this was all for today's session. Thank you.